Hello everyone, welcome to SJC content. This is Dr.L.JETHRUTH EMELDA Mary, Assistant Professor in Mathematics, St.Joseph College of Arts and Science, Autonomous, Cuddalore, Tamil Nadu. In this video lecture, we are going to discuss about revised simplex method in mathematical programming for first MSc Mathematics. Revised simplex method has two forms. One is called standard form 1, another one is called standard form 2. Before discussing the reverse simplex concept, let us see what is the advantages of revised simplex method. Every linear programming problem can be solved using simplex method, graphical method, artificial variable technique, and two-phase method, dual simplex method. Here, the revised simplex method is the best method when we compare with the above said methods, which gives the accurate solution or the best solution comparing with the remaining methods. So let us see the revised simplex method to solve linear programming problem using standard form 1. What is standard form 1? The standard form 1 is nothing but is a method of revised simplex in which we shall form identity matrix after adding a slack or surplus variable only. No need to add artificial variables. Whereas in standard form 2, the artificial variables are added to have identity matrix, and then two-phase simplex method is used to handle artificial variables but in a different manner. Now we are going to see the revised simplex method in standard form 1. In this method, the objective function is also treated as another constraints, and the standard form is given by z minus c1 x1 minus c2 x2 etc minus cn xn minus 0 xn plus 1 minus 0 xn plus 2 plus etc minus 0 xn plus m equal to 0. A11 x1 plus A12 x2 plus A13 x3 etc. A1n xn plus A1 into xn plus 1 equal to B1. Third equation is A21 x1 A22 x2 plus etc. A2n xn plus 1 xn plus 2 etc. is equal to B2 etc. An plus 1 x1 plus an plus 2 x2 plus etc. an plus 1 xn plus xn plus m equal to bm. For all x1, x2, etc. xn plus m greater than or equal to 0. So this linear equation, the system of linear equation can also be represented in the following notation. We call it as a matrix notation. Z minus cx equal to 0, ax equal to b for all x greater than or equal to 0. That is, it is 2 cross 2 matrix 1 minus c 0 a, where minus c is the cost value of the base variable and 1 is the coefficient of z and 0 is the coefficient of z, the next row, where capital A is the capital A represents the coefficients of all the constraints or coefficient matrix, and x is nothing but a column matrix z and x, where x is equal to the row matrix, transpose of a row matrix x1, x2, etc. xn, that is equal to 0b for all x greater than or equal to 0. Now, by taking z equal to x naught and minus cj is equal to a naught j, we have the symmetric notation of the above equations, that is 1 into x naught plus a naught 1 x1 a naught 2 x2 plus etc. a naught n xn plus etc. a naught n plus 2 xn plus 2 etc. and a naught n plus m xn plus m equal to 0. The second equation is 0 x naught plus a11 x1 plus a12 x2 plus etc. a1n xn plus 1 xn plus 1 equal to b1. The third equation is 0 x naught a21 x1 a22 x2 plus etc. a2n xn plus 1 xn plus 2 is equal to b2. etc. The last equation is a 0 naught, that is 0 x naught plus a n1 x1 a n2 x2 plus etc. a n m x m xn plus xn plus m equal to bm, where this xn plus 1, xn plus 2, etc. xn plus 1 are the slack variables which are added in the constraints, and x0, x1, x2, etc. xn plus 1 are greater than or equal to 0. Now we shall represent the above equations again in the symmetric matrix notation in the following manner. So all the first column of z, the coefficient of z is taken in the first column, and coefficient of x1 taken in the second column, coefficient of x2 taken in the third column, etc. In the similar manner, the coefficient of xn plus 1 are written in the taken as the final column of this matrix. So which is represented in such a way that 1 0 1 a01 a02 a0n etc. a0n plus m. The second row is represented as 0 a11 a12 etc. a1n 1, then all other values are 0. The third row is represented by 0 a21 a22 a2n etc. a2n 0 0 1 etc. 0. Then the last column, the last row or the last row of the matrix is represented by 0 an plus 1 an plus 2 etc. an plus m or am plus m 0 etc. last value will be 1. Here the order of this symmetric matrix will be, there are m plus n columns, therefore we shall write this as m1 plus m plus n cross n plus m, and the variables x can be written as the column matrix x0 x1 x2 etc. xn plus m, that is equal to b, where b is in the form of column matrix 0 b1 b2 etc. bm, or just we can write the short form, the matrix 1 a0 0 a into x0 x, that is equal to 0 b. What is a? Small a0 is equal to the column vectors or the row vectors a01 a02 etc. a0 m. So now we shall see the procedure following with the examples. Let us consider the following example. Use the revised simplex method to solve the following LP problem. Maximum z equal to 2x1 plus x2 plus subject to the constraints 3x1 plus 4x2 less than or equal to 6, 6x1 plus x2 less than or equal to 8. Now we shall write or express the given linear programming problem into standard form. We are going to use the standard form 1 revised method, using revised simplex method. So for that, let us consider the objective function as one of the constraints and add a slack and surplus variable if needed to convert the inequalities into equalities. So therefore the given equation, namely we call it as a linear programming problem, can be written in the following manner: z minus 2x1 plus x2 minus x2 equal to 0, and 3x1 plus 4x2 plus s1 equal to 6, 6x1 plus x2 plus s2 is equal to 3, where x1 x2 s1 s2 greater than or equal to 0, where z is unrestricted in sign. So now we shall represent this what is called the system of linear equation or system of equation in the matrix notation or matrix form. 1 minus 2 minus 1 0 0 0 3 0 1 0 0 4 0 0 1, where the first column represents the coefficient of z1 and second column represents coefficient of x1 and the third column represents coefficient of x2 and the fourth column represents coefficient of s1, the last column represents coefficient of s2. So these values are namely the all the columns are denoted in the form of e upon 1, a1 upon 1, a2 upon 1, a3 upon 1, a4 upon 1, and the column matrix x can be written as z x1 x2 s1 s2, that is equal to right hand side column matrix is taken as 0 6 3, where e upon 1 can be taken as beta naught upon 1, and the namely the slack variables, the last column as well as fourth column can be taken as beta 1 upon 1, beta 2 upon 1, where this represents the column matrix of s1 and s2. here let us take b1 is equal to beta naught upon 1, beta 1 upon 1, beta 2 upon 1. This is the which represents the column matrix corresponding to the column, namely the first column is Z and the slack variable S1 and last one is slack variable S2. Now we shall obtain the initial basic solutions. So for that we start with B equal to IM, where I is the identity matrix of order M. Here there are two constraints. So IM is equal to identity matrix of order 2. So let us be here B is equal to 1 0 0 1. Which is nothing but A3 upon 1, the fourth column, that is the column vector A3 upon 1, A4 upon 1. And by according to the definition, B1 inverse is nothing but the matrix 1 CB B inverse 0 B inverse. What is CB? The cost value of the basis, nothing but 0, the column matrix 0 comma 0, the whole transpose. Now the initial basic feasible solution is nothing but S1 equal to 6, S2 equal to 3 by taking x1 and x2 equal to 0 and maximum z is 0 only. Now we have the corresponding table iteration, the revised simplex table. In the first column, let us take the basis variable. We take the basis variable as z s1 s2 and the solution values are taken as already you know that the B column 0 6 3. Then and basis inverse B1 inverse is B0 upon 1, B1 upon 1, B2 upon 1, which is nothing but the column vectors Z, S1, S2, whose values are namely 1 0 0, 0 1 0, 0 0 1, namely it is a identity matrix of order 3. And the last column is YK upon 1, which can be denoted as CK minus ZK. And the next table we call it as additional table, which contains only the non-basis variable. The corresponding variables are x1, x2. The column vectors are a1 upon 1, a2 upon 1, whose values are -2, 1 0, 1 6, -1 4 1. Now we have to find B1 inverse as well as B1 inverse B to form the initial revised simplex table. So in step 3 is we select a variable to enter into the basis, namely a key column. For that we need to calculate CK minus ZK, which is nothing but CK minus CBB inverse AK upon 1, where B1 inverse AJ upon 1 represents the product of the first row of B1 inverse and the successive columns of the matrix, namely we call it as additional matrix A, which is not in the basis B1 inverse. In case Cj minus Zj is less than 0 means then the current solution we call it as an optimal solution. Otherwise you have to go to step 4. If one or more Ck minus Zk are positive, then the variable to enter into the basis may be selected by using the formula Ck minus Zk equal to maximum of Cj minus Zj, for which Cj minus Zj greater than or equal to 0. So for that let us compute the following manner. Ck minus Zk equal to maximum of Cj minus Zj greater than 0 when j equal to 1 comma 2. The maximum Cj minus Zk can be calculated by using the formula already know, the first row of B1 inverse into the successive column of matrix A, which is not in the B1 inverse. So the first column, namely the first row of B1 inverse matrix from the previous table is 1 0 0, and the additional columns of A, which is namely we call it as the additional table, is -2 3 6, -1 4 1. So this is comfortable to take the multiplication, matrix multiplication, because the order of the first matrix is 1 cross 3 and the order of the second matrix is 3 cross 2. Hence it satisfies the matrix multiplications, the condition of the requirement. Hence the resultant matrix is minus of -2 comma -1, that is equal to 2. So maximum value is 2. Everything is positive, so you cannot conclude this is an optimal solution, because our aim is to find the Ck minus Zk, namely Cj minus Zj less than or equal to 0. Here all Cj minus Zj values are positive, therefore we must move to the next iteration. So for that let us select the variable or the vector a1 upon 1, namely x1 is a variable which is selected to enter into the basis for the next iteration for k equal to 1. In step 4, we select a variable to leave the basis, we call it as a key row, For that, we need to calculate yk upon 1 in the formula b1 inverse ak upon 1, that is equal to ak upon 1, because b1 inverse is already identity matrix. When you multiply any identity matrix with any column vector, we get the same column vector. Therefore, b1 inverse ak upon 1 is nothing but ak upon 1, where ak upon 1 is nothing but minus ck comma ak. If all yik is less than or equal to 0, then the optimal solution is always unbounded. We have already seen in the simplex method, isn't it? So whenever yk is less than or equal to 0, the optimal solution is unbounded. If at least one ik is greater than 0, then the variable to be removed from the basis is determined by using the following formula: xbr by yrk equal to minimum ratio xbr divided by yik, for which yik greater than 0. That means the value yik should be positive. So only for that value you have to find the minimum ratio. Here the vector br upon 1 is selected to leave the basis and go to step 5. If the ratio is same for more than one row, then the resulting basis feasible solution will be degenerated. So for that, let us compute yk upon 1 using this procedure. Just we calculate y1 upon 1 for k equal to 1, that is b1 inverse a1 upon 1, that is equal to ba1 upon 1, that is the column matrix which is not in the basis. We call it as additional table. The first column of the additional table is nothing but a1 upon 1, which is nothing but minus 2, 3, 6, and xb upon 1 is b1 inverse into b, where b1 inverse is identity matrix into b. Therefore we'll get the same matrix b, which is nothing but 0, 6, 3. Now we find out minimum ratio xbr by yrk. We call it we calculated by using the formula minimum ratio y xbr by yik, for which yik is greater than 0. So using that, we have minimum of xb1 by y11, xb2 by y21 for k equal to 1, that is 6 by 3. xb1 is 6 and y11 is 3. Similarly, the second value is 3 by 6. Using this, you will get the minimum ratio is 3 by 6, that is 1 by 2. This is beta 2 upon 1, namely the corresponding to S2 variable. So here we say that S2 is the leaving basis variable. We select S2 as the leaving basis variable. Now the following table gives the computed values, the new values, namely the basis variable Z, namely B, the Z column, B column, the basis variable B, Z, S1, S2, and the solution value B is 0, 6, 3, and basis inverse B11 is this. We've just fill CK minus ZK column, which is minus 2, 3, 6, and the minimum ratio is 6 by 3 and 3 by 6. So the rounded value is known as in the third row of this table is called the leaving basis variable. So in step 5, just we update the current solution. For that, we have to introduce a non-basic variable xk, that is ak upon 1, into the basis, and removing the basic variable xr, namely br upon 1, from the basis. So we have to repeat this procedure or repeat these steps from 3 to 5 until an optimal solution is obtained, or there is an indication for an unbounded solution. So for that, just we replace the variable s2 with the variable x1 in the basis by applying new row operations in simplex method, which we discussed already in the simplex method. So we are calculating new r1, new r2, new r3 using this formula. We obtain this for column values in the following table. The improved solution table is this. The basis variable B is Z, S1, X1, and in the second column solution values 1, 6 by 2, 1 by 2. The remaining values which I have calculated in the previous steps that are taken in this taken into consideration. It is represented in this following table: new R1, new R2, new R3. Here again we repeat the same steps from 3 to 5 to get the new improved solution. So for that, we just determine the new table. It should be remembered that column beta naught 1 will never change it, and also the entries in xb upon 1 y1 upon 1, beta 1 upon 1, beta 2 upon 1 columns will be changed due to the above mentioned row operations. So for that, select the, similarly we are going to select the corresponding non-basis variable to enter into the basis. For that we just calculate ck minus zk, which is nothing but maximum of cj minus zj is greater than 0 for j equal to 2 comma 4 only. Here, so that can be calculated as usual by using the formula minus into the first row of first row of matrix B1 inverse into additional table, additional matrix. So from this we get 2 by 3 is the maximum value. Here all the values are negative, positive. So the maximum value is 2 by 3. Thus the vector a2 upon 1, namely x2, is selected to enter into the basis for k equal to 2. So in step 4, just find beta r upon 1 corresponding to the basic variable to leave the basis. So for that we calculate y2 upon 1, namely b1 inverse a2 upon 1, that is also a2 upon 1 because b1 inverse is already identity matrix. So just we find out this values, we compute the value b1 inverse a2 upon 1. By multiplying we get 3 cross 1 row, 3 cross 1, the order of the matrix 3 cross 1 minus 2 by 3, 7 by 2, 1 by 6. The minimum ratio is xbr by yrk. That can be calculated by as usual manner by omitting the negative value, by taking only the positive value. Just we use the formula. Here we found that 3 by 6, the corresponding variable is s1, is selected to leave the basis. So in step 5, just update the solution by replacing the variable s1 with the basis variable s2 into the basis, and then we found out usually the new go to the next iteration means we determine the new rows r1, r2, r3 with the help of the above table, and we get the following table. The improved solution is basis variable b. In the first column we have z, x2, x1, and the solution variable b is 13 by 7, 9 by 7, 2 by 7. So all these values are updated by using the above calculations. So again we repeat this step from 3 to 5 to get the new improved solution. For that we need to check the condition ck minus zk. Maximum of cj minus zj is greater than 0 for j equal to 3 comma 4, third and fourth column. So this is one of the additional table that can be calculated by using again maximum of minus first row of b1 inverse into additional table. That can be calculated by using the same formula, and we found that all cj minus zj is less than 0 here for j equal to 3 comma 4. Hence we can conclude that the current solution in the above table is optimal. Therefore the optimal solution for the given problem is maximum z equal to 13 by 7 when x1 equal to 2 by 7 and x2 equal to 9 by 7. Thank you students for watching this video.